Thanks a lot for the invitation to speak. I'm really sorry I can't be there. I really wanted to be there. You have no idea how much I wanted to be there. But in any case, I'm not there. So this is the first of 5 lectures basically on cohomology of arithmetic groups and various computational aspects of them and experimental results, connecting them to arithmetic geometry and other things. And the focus is really sort of to complement what's happening in some other talks. I want to try to, well, first of all, focus on sort of higher rank examples, at least for the most part. And I also want to talk some more about the connections to arithmetic geometry and representation theory and so on. So this first lecture is going to be pretty, actually I should go to the next page here. So here's, the first lecture is really, the first 2 and 1.5 lectures or so is really just going to be sort of an overview about cohomology of arithmetic groups and its various ways to think about it and various approaches to it. So it might be sort of redundant to what you've heard in some other things, but I hope not. Or if it is, it's not always so bad to be redundant. And then for the next part of the talk, next part of the series will be more about sort of getting down and dirty with the explicit reduction theory, and that will complement what Philippe is going to be doing in his lectures, and should also be very closely related to things that you've seen in last week. And then we'll talk about computing Hecke operators and some of the techniques that we use to do that, and what Hecke operators are, why you want to compute them, and how you might go about it, and some various things that could be worked on in the future in that. And then finally, since its lectures are in France, I think everything has to have a section called complements, although I don't think that's how you say it, but I think that means anything I want to do. So I'll save that, reserve that for later, and hopefully we'll see how it goes when we get there. Okay, so first of all, why does one care about the cohomology of arithmetic groups? So first of all, I mean, it's cohomology of groups. You know, that's sort of an end in itself. A lot of people are interested in that. This is a very sort of special type of group. Why would anyone care about this? Well, first of all, just as a subject, without any thought about what applications and things like that are, it's a very interesting subject because it involves so many different parts of mathematics. It really sits at the intersection of a lot of different fields. There's a lot of different ways to get into it and a lot of different tools and techniques that you need to sort of understand, to be able to read the literature and to do computations, prove new results. So you have to know a lot about algebra, topology, geometry in the sense of like differential geometry, representation theory, and number theory. It's wherever you go, whatever you're doing with this subject, you're bound to run up against something that has some interesting thing to do with some field. It just seems like it's almost maybe not. I mean, I'm not going to say that there's not some field that has no relevance, but it's just very amazing how it involves all these different things. One of the key things that it involves is automorphic forms. So you've heard a lot about, I'm sure, about modular forms, holomorphic modular forms, and maybe perhaps some other generalizations in other settings. But the connection here is that in a certain sense, when you're computing a cohomology of an arithmetic group, you are explicitly working with certain automorphic forms. In the case of SL2 over Q, those are going to be the classical modular forms that you know and love. But for other groups, they're more exotic modular forms that you maybe have never seen, and this may be the only way to sort of get your hands on them explicitly, to work with them. So it gives a very concrete way to compute with such things. The next thing is that, well, they are called arithmetic groups, so there should be some relation to something to do with arithmetic. And yes, arithmetic geometry also is very important in the subject. And you know this from, if you've studied modular forms, you know that weight 2 modular forms with rational Hecke eigenvalues are very closely related to something in algebraic in arithmetic geometry, to elliptic curves. And this in general is true, although it's not exactly said that way. It's said in terms of Gauss representations, but you've seen some of that, I know, this morning. Well, morning for me, not morning for you, but in Haluk's talk. And we'll see more about this later on. From the geometric and topological side, there are a lot of really interesting spaces that are involved when you look at this. Locally symmetric spaces, modular varieties, and compactifications of these things. And some of these spaces are among, I think, the most interesting spaces that you're ever likely to run across ever. I mean, the geometry and topology is so intricate and so complicated, but they're really beautiful. They have a lot of beautiful things that you can look at with them. And even beyond arithmetic geometry, there are other arithmetic applications. So as you're going to hear about from Philippe, applications to K-theory. There are also applications to multiple zeta values, which are sort of generalizations of the special values of the Riemann zeta function to sort of higher dimensions, and polylogarithms. And they're very surprising ways in which sort of applications to arithmetic appear in these things. And so hopefully if I have a chance in the complements, I can talk about some of the last two things there, since Philippe is going to be talking about K-theory. The arithmetic plays a strong influence in the cohomology and sort of in surprising ways. So I'm talking beyond, not talking about connections between cohomology and arithmetic geometry. I'm talking about when you're trying just to study the cohomology, just try to compute it or try to understand its structure. For example, there could be cohomology classes that you try to make, and whether or not those classes exist and give something non-zero could depend on special value of some L function. So if that L function has a 0 at some point or a pole somewhere, then you can, that influences whether or not a cohomology class exists. And because of the connections to geometry, I mean, this maybe sounds like a tautology, geometry influences cohomology, but it's not, in the sense that there's, using these spaces, they're not just sort of random manifolds or random spaces. They have a lot of structure about how they're built, and you can use that to try to produce interesting cohomology, interesting homology. So, I mean, I was thinking here when I wrote this, something like the Hirzebruch-Zagier series cycles on Hilbert modular varieties, and just how those are built, and modular symbols and generalized modular symbols. So there's lots and lots of things to say about that. Okay, so I want to start from I just want to assume basically that nothing about what you might know or not know. So if this is a review or uninteresting, I'm sorry, but I know that at least for some people it won't be. But in any case, let's start sort of at the beginning. So we have to get off the ground, we have to have algebraic groups. So I want to at least tell you what they are. I'm going to take a very sort of low level approach to algebraic groups. I'm not going to do everything in the most generality. I just want to try to give an idea for people who maybe have never seen them or only lightly seen them before. So we're going to have G is going to be a connected linear algebraic group defined over Q. So what this means is, so first of all, G is an affine algebraic variety. It is given by an ideal in a polynomial ring. In the polynomial ring, I'm just going to take complex coefficients just to make it easy. So the polynomial ring has variables given by indeterminates xij, which you just think about as being entries of an indeterminate matrix, n by n matrix, and also another variable d. So d is take the polynomial, the determinant in this indeterminate matrix, and then invert it. So we're going to only work inside. We're only allow, if we omitted this d inverse, we would just have just the polynomial ring of the space of matrices in some sense. But we want to make sure that we have invertible things, so we add this extra variable, this inverse. And now we require, it's an algebraic variety, but we require that the multiplication And inversion maps are morphisms of algebraic variety. So that just really means that they're given by polynomial functions in these variables. So essentially polynomial functions in the matrix entries. And you know that from the way matrix multiplication works. That's true in inversion because we have this D inverse in there. We're good with that. Okay, we can regard this ring R, this sort of beginning ring, as the coordinate ring of GLN. So what we're really thinking of is this group G is a subgroup of GLN. It's defined by polynomial equations. Okay, and there's lots of examples I'm sure immediately coming to mind, and I'll talk about some more in a second. What about the defined over Q part? So that's very simple. It just means that this ideal has to be generated by rational polynomials. So the polynomials have to have rational coefficients. And finally, connected means that G is connected as an algebraic variety. Okay. So there's some terminology that you see very often when you're trying to read papers in the subject, reductive versus semi-simple algebraic groups. These are sort of the most important examples for these applications. So first of all, we say an algebraic group is unipotent if it's isomorphic to some closed subgroup of the n by n upper triangular matrices with ones on the diagonal. So that's sometimes noted as UN, not beware, there's other groups also denoted UN, but it's not the same, as you'll see. But in any case, that's what it means to be unipotent. And we say that the radical of an algebraic group is the identity component, the connecting component of one, of its maximal normal solvable subgroup. And then the unipotent radical is just the subgroup of the radical consisting of the unipotent elements. And finally, we say that it's reductive if this unipotent radical is trivial, and semi-simple if the radical is trivial. Okay, so that's a lot of terminology. Let me show you just how it works. I mean, in practice, it's a lot easier to deal with than trying to unwind all this terminology. So the most basic example is, of course, GLN and its favorite subgroup SLN. So GLN is reductive. The radical is the subgroup of scalar matrices. So the diagonal matrices where everybody is the same, and of course they have to be non-zero. And there's certainly no unipotent elements in there. So there's no, its unipotent radical is trivial. SLN is semi-simple. So to be a scalar matrix in SLN, well, the determinant has to be one. That's the definition of SLN, should have said, just assume you knew it. But that means that the product of these A to the n has to be one. So A has to be an nth root of unity. So the connected component in that case is just the identity matrix. So that's why it's semi-simple. So here's some examples, just to help you picture it. So of course, we just talked about SLN. So we have SP2N, this is the symplectic group. So these other groups in this list, except down at the end, these are constructed by starting with, so SLN acts on vector space, n-dimensional vector space. We take that vector space and we put some extra structure on it, and then we ask for the matrices that preserve that structure. So SP2N comes when you put a non-degenerate alternating bilinear form on your vector space, and you look at the subgroup of GLN that preserves that alternating bilinear form. Okay, and the orthogonal group comes from putting a symmetric bilinear form. That's the next one, ON. And after that, we have OPQ. So then you can take a bilinear form of signature PQ. So it looks something like x1 squared up to, well, x1 times y1 plus ... up to xp, yp. And then you have minus signs for the next ones up to xq, yq, that bilinear form. And next we have the other UN, the unitary group and special unitary group. So these are the matrices acting on a complex vector space that preserves a non-degenerate Hermitian bilinear form. And then finally we have the determinant one versions of those for SUN. And we can take products. These concepts are closed undertaking products. So for reductive, there's just slightly different. We have examples like these. So GLN, the difference between GLN and SLN is, of course, you can have an arbitrary determinant as long as it's non-zero. So what's the difference between GSP and SP? So this GSP is sometimes called the symplectic similitudes. What this means is that you take the matrices that don't preserve the alternating bilinear form, but they preserve it up to some multiplication by some scalar. So the analog of having a sort of general determinant is now replaced by, you don't have to take that bilinear form into itself, but you have to preserve it up to some scalar. And then you have similar things for the orthogonal group and unitary group, similar kind of notion. And you can take products. And so a very basic example that's comes up all the time is if you take products of GL1. If you take products of GL1, that's a special kind of algebraic group called a torus. And it's not the torus that you're maybe used to. I mean, the torus that you're used to looks like a product of circles. This is sometimes called the algebraic torus, or if you like, non-compact torus. Okay, now what about, those are all examples of those two. What about things that are not? I mean, just because you have these two doesn't mean you're not going to have these other things. These show up all the time in part of the structure. So these are all just going to be thought of as subgroups of GLN. So there's the unipotent group that we already mentioned. And then we have what's called the Borel subgroup, standard Borel subgroup. These are just the upper triangular matrices. So they don't have to have ones in the diagonal. And next we have what are called standard parabolic subgroups. So if you take a composition of n, meaning some way to write n as an ordered sum of things, and you assume that you have more than one part, then you can make a proper subgroup of GLN, which are the block upper triangular matrices, where the block sizes going down the diagonal are given by the parts of pi. And notice that each one of these p pi's contains Bn. So it's sort of a generalization of Bn where you allow more interesting diagonal. And these are not reductive and they're not semi-simple. So first of all, they have a unipotent radical. The unipotent radical of Bn is actually Un. And the unipotent radical of these p pi's is sort of a mild generalization of that. We'll talk about it later, maybe. Okay, so how do you think about it? I mean, the basic heuristic, which is false, okay, is that a reductive is basically a semi-simple group times a central torus, meaning a torus that commutes with everybody in the semi-simple group. So, and if you think about it, this is sort of a pretty reasonable way to think about it. It's not exactly right, but it's not that far from being the truth. If you think about GLN and SLN, the only difference between GLN and SLN is the determinant. So it's basically like you have SLN, then you have this extra number that records the determinant. But of course, it's not exactly how GLN and SLN work. So the truth is that any reductive group is almost a product. In fact, it's called an almost direct product. You take a semi-simple group in a central torus, and they are allowed to intersect in some finite central subgroup. And then you take the quotient by that. So for example, for GLN, you can take SLN and then just take GL1. So here I'm thinking about those are the scalar matrices. And the intersection of that GL1, so SLN does have a center, and that center is mu n. So we have to divide out by that. Otherwise, we're going to have something too big. So it's, I mean, when I was learning this stuff, I always found like the definition of reductive and semi-simple and all this stuff to be kind of opaque. But in reality, it's not, in practice, it's not that hard to deal with and usually not that different from things you already understand pretty well anyway. Okay. All right, and there's another concept that we're going to use and comes up quite a bit in algebraic groups. It's called restriction of scalars. So suppose we have a number field like Haluk was talking about. We're definitely going to want to consider algebraic groups where the matrix entries live in a number field. So if you think of the group GLN, this unfortunately is not an algebraic group defined over Q as we've written the definition down, because the matrix entries, they're in F. We need those polynomials that define the group to have rational coefficients, and it's not exactly going to be, if you just sort of naively write down GLN F, it's not going to be what we're looking for. But there's a standard way to deal with this that, again, when you see this all the time in literature, it feels a bit opaque and a bit hard to understand, but it's actually quite simple. And this is this idea of restriction of scalars. So for any algebraic group, this is defined over F, and that's sort of the natural way to write down GLN of F. You can imagine how to change the definition that I wrote before to have it being defined over F. We get an algebraic group that's actually defined over Q called RF, the restriction of scalars from F to Q of G. It has this property that the rational points of that group are the same as the F points of this original group. So we can use it in this case. If I apply this to bold G being GLN, I make a group that just is defined over Q. It's polynomials that define it have rational coefficients. But when I take the rational points, I look at the rational solutions to those polynomials, I end up making this group of that I want, GL and F, to get the F solutions somehow. So it turns out that's something that you've probably seen a lot of times and not realizing that's what you were looking at. So here's how it works. So you imagine you wanted to do this just for the field itself. Take a basis x1 up to xd of the field as a vector space over Q. I mean, any number field is a vector space over Q. So we just take a basis. And then we can convert any element of the field into a D by D matrix over Q. For D, this is the degree of F over Q, obviously. So what do? So I just take this element Y and F and I multiply it on these basis elements one at a time and then rewrite them in terms of the original basis. So the ith column of that matrix is just going to be multiply xi by y and then write it in terms of the xi, x1 up to xd. So here's the example that everybody has undoubtedly seen, although maybe with real coefficients and not rational coefficients. If you take q adjoin the square root of -1 and then take this obvious basis, you can take the element a plus b times square root of -1 to this matrix. This is exactly what happens. When you multiply that guy by 1, you get the first column, a plus b times square root of -1. Multiply by the second guy, then what happens is the a shifts down and you get a minus b on the top. Any matrix on the right-hand side where a and b are rational numbers, you multiply them, add them, behaves exactly the same as if you're doing it on the left-hand side with those numbers in that field F, okay? So now if you want to do that for groups, to make a group, you just have to do this kind of entry by entry in the group. You want, if you want things, you want rational things that are reproducing F things, you're basically doing this for every element F in the group. In fact, if I wanted to make GLN over F, I could just do this as I've written and just make a big matrix of ND by ND with those rational numbers. Now it's not every group is GLN, so there could be some equations that that you have to use to define the group, like SLN, determinant 1. So you have to modify the equations as well to make them rational. But it's not so bad, and it's better. I mean, you can write something out. I mean, the place that I've seen it written out in explicit detail is Platonov and Rapinchuk's book on algebraic groups. And by the way, I will give, I don't give really many references in the talks, but I'm preparing a list of references to distribute at some point when I'm finished everything. I'll make sure that's in there. It's actually a lot easier to figure it out yourself than to try to read someone else's description of it. So I think it's better to go and just try to work this out for SLN, even for this example of this field, and you'll see exactly what you have to do to make it work. Okay, and again, this is kind of a lowbrow description of what restriction of scalars is, but it's excellent for practical applications, and it's really what's going on. So you don't necessarily learn more by trying to make it super fancy. But anyway, that's what it is. Okay, now that's really all I want to say about algebraic groups. Let's talk about arithmetic groups. So an arithmetic group is a discrete subgroup of GQ commensurable with GC. So commensurable just means two groups are commensurable if both of them have finite index in their intersection. Okay, so for example, we could take GZ itself, just take all the integral solutions to those equations, and they give you a subgroup, and that is an arithmetic group. Or I could take any conjugate. So you might think, well, why don't I just take subgroups of GZ? Well, it's sort of easier technically to allow yourself to have more flexibility and to have this commensurability definition. But it's, if you want, most of the time, we're really just going to be working with subgroups of GZ anyway. But here's another example. Okay, so here's some more examples. So let's take G to be SLN over Q. Okay, so determinant one matrices with rational entries. So that the rational solutions to that are just SLNQ. And then if I take gamma to be SLNZ, that's an example because the G's, that's exactly just GZ. And that's certainly a big, interesting group that we're going to have quite a bit to say about, hopefully. And you're going to definitely learn a lot more about that group this week. So to get more examples, talk about what's called congruent subgroup. So I define gamma of n, where big N is some integer, as a subgroup of SLNZ to be the subgroup of matrices congruent to the identity mod n, okay? So that is finite index because if you take the quotient of SL little nz by gamma of n, you wind up with the finite group SL little nz with coefficients in the z mod nz big N, okay? This is called the principal congruent subgroup, sort of the main one. In general, we say a subgroup is called a congruent subgroup if it contains gamma of n for some n. And it has this great feature that it's torsion-free. So SLNZ contains a torsion-free subgroup of finite index. That's sometimes called virtually torsion-free. So one question you might ask is, well, that's a big class of examples, the congruent subgroups. It's not every subgroup of SLNZ a finite index if little n is equal to 2. There are non-congruent subgroups there. For n bigger than or equal to 3, little n, all finite index subgroups of SLNZ are congruent subgroups. But there is something special that happens for SL2. Okay, we can get a generalization of that by looking at a different congruence condition. So you're probably familiar with this group from little n equals 2. It's called gamma naught of n. You take the matrices of your n by n matrix and you require them to be congruent to that, the bottom row to look like that when you work mod n, okay? So that's exactly what, the same definition when little n is equal to 2 from what you're used to, but we have generalization now to bigger n. And this is sometimes called the Hecke congruent subgroup. And we can vary this in a lot of different ways. So we could take lots of other kinds of congruence types and impose this kind of condition like we did for the Hecke congruent subgroup. We can take any block triangular form. I'm just saying here, just take the matrices, take this composition of n as before for p pi, and then look at the matrices that have the same block structure modulo n as that guy, okay? So this example in the one before was the composition was n minus 1 n. And these are all congruent subgroups because they all contain the principal congruent subgroup for the same n. What about over number fields? Well, if we take a number field and we have the ring of integers OF, apologize for using this notation in France, but like I said, I'm in my basement, so I can do whatever I want. And then we let G be the restriction of scalars from F down to Q of SLN, okay? Then the way the restriction of scalars works, the rational points of this group GQ are SLNF, and then the integral points are SLN over the ring of integers, okay? So you can kind of see why this restriction of scalars at least is notationally useful. You don't have to keep changing what you're plugging into the parentheses there. You get to work with Q and Z all the time. And just like we had for SLNZ, we can talk about congruent subgroups. We can fix an ideal in the number field in the ring of integers, and we can look at matrices that are congruent to the identity mod n. That would be the principal congruent subgroup, and then we can take block shapes and look at those and get variations on that, all kinds of stuff like that. And these are all examples were all for SLN, but we can do similar things with other groups. So we can write down congruent. For example, if you can do this, say you wanted to do it for SP2NZ, how could you do it? Well, one thing you could do is just sit it inside SL in SL2NZ. Think of it as a subgroup of that, and then take the intersection. There could be more interesting ones than that. There could be more complicated ones. For example, there's something called the paranormal subgroups of SL of SP2N. So there definitely things get different when you get away from the easy world of SLN and GLN, but you can still work it out, and it's not that difficult. You may have to write down some conditions on your entries that look more intricate than what we're talking about, and they may look different from just being modulo something. They may involve inverses of numbers. It's interesting, so we'll take a look at. So, okay, so those are the arithmetic groups. We're headed for cohomology, but we're gonna, since our approach is primarily topological, I need to talk about the spaces that we use to actually do computations with. Okay, so let's take an arithmetic group, and I'm going to build a space that I can use to compute cohomology with, and it's going to be called a symmetric space. So how do I do that? So first of all, I take the group of real points. So I have my algebraic group, and now I look at the real solutions to that. That is another group. It's a Lie group. So it is a smooth manifold that has the structure of a group where the group operations are infinitely differentiable. Okay, Lie group. And inside there, I have what's called a maximal compact subgroup. And those so we're going to do examples in a moment, but you can probably imagine them already. The next thing is a little maybe more obscure. You don't always see this because a lot of times we're only dealing with semi-simple things, but it's called the split component. So it's a mouthful to say what it is, but here it is. You take the connected component of the group of real points of the maximal Q-split torus in the center of G. Okay, so a Q-split torus means it is a group, so it's GL1, a product of GL1s that over Q is isomorphic. The rational points are just isomorphic to the same number of copies of Q cross. So it just, it's Q point, it's a copy, I'd say a copy of D GL1s that over Q looks like Q cross to the D. Okay, so we want to look at such a thing in the center of G, and then we take the group of real points and take the connected component of the identity. I'll give you an example in a moment, but then when we take the quotient of G divided by AGK, we get what's called a global symmetric space. So topologically, it's not very interesting. It's just homomorphic to Euclidean space. But it is much more interesting from geometric point of view, from differential geometric point of view, because it has a natural metric on it. So there's an action of G on that space just by multiplication on the left. And there you can write down an invariant metric on there. Makes it a lot more exciting than just Euclidean space. So here's some examples just to get started. So these are all semi-simple examples. So you're not going to see much in the AG, but they at least are going to be relatively familiar. So the one that should be familiar to everyone is when you take SL2 over Q. Okay, so then the Lie group in that case is SL2R, and the maximal compact subgroup is a special orthogonal group. So these are the 2x2 matrices, such that if you multiply them by their transpose is their inverse. So A times A transpose is the identity. That's the largest compact subgroup up to conjugacy by elements of SL2R inside SL2R. Okay, and then if you take, let's say AG is 1, so what is the center in this case of SL2R just consists of the diagonal matrix, the identity, and also -1, -1. So there's no central, no rational torus sitting there. So the connected component of the identity is just 1. And the symmetric space in this case is the upper half plane, the hyperbolic space, two-dimensional hyperbolic space. If you generalize this to bigger N, well, you just get SLNR for your Lie group and SON for the maximal compact subgroup. And it doesn't have such a standard name, but it does have an interpretation, as we'll see later. It's related to sort of a different way of thinking about it than just this quotient G divided by K. It's related to a space of quadratic forms, positive definite quadratic forms and N variables. For the symplectic group, the group of real points is unsurprisingly SP2GR. The maximal compact subgroup is a unitary group, UG. There's no split component, and this time the symmetric space is sometimes called the Siegel upper half space of genus G. So these two here, SLN and SP2G, are really two different ways of generalizing the thing on the first line. So when G is equal to 1 in the third line, you get SL2. But there's the two different ways to build off of that, both emphasizing different structures. And now, example you definitely heard about this morning. So if I take the restriction of scalars of SL2 and I take an imaginary quadratic field, then my Lie group is SL2C. This is the group of real points, but because we have an imaginary quadratic field, we don't get SL2R. You know, if you tensor with R, you're going to get SL2C. So that's the Lie group in that case, and the maximal compact subgroup is a special unitary group. And this time, the quotient is D is hyperbolic 3 space. Okay. So here's to illustrate the difference between the semi-simple and reductive case. So if you take a totally real field, degree D, then the Lie group for SL2 is going to be D copies of SL2R. So where this is coming from is that you can see it sort of in the next line, the general case. So if F tensor R is R to the R times C to the S, if R real places and C and S complex places, then you're going to get that many copies of SL2R and that many copies of SL2C. So that's why we're getting D copies of SL2R up here. And the maximal compact subgroup, each one of them is SO2, and we have D of them. So we just get a product of D hyperbolic planes. When we do GL2, now finally we do have a split component. We have a non-trivial split component, okay? So the maximal torus inside GL2 that is in the center is going to be just putting a copy of Q in each, the scalar matrices with rational entries sitting inside GL2, okay? And so the connected component, the real group of real points of that is just going to be R cross, because you can just complete it to R, but then the connecting component of the identity is the things bigger than 0. So it's just a copy of R plus that you have sitting there. So the difference now is that, see, GL2 is much bigger than SL2 because of the units. You have units in GL2 over the ring of integers of F that you don't have in SL2. And the symmetric space has to accommodate that in some way, so it's much bigger. We have not just D copies of the upper half plane, but we also have this extra copy of R to the D minus 1. So it's coming from the units. And that's what happens in general for a number field. So if you look at SL2, you're just going to get R copies of the upper half plane for the R places, for the real places, and S copies of the hyperbolic 3 space for the complex places. And in the GL2 case, you have that, but then you also have something for the units, because the units have rank R plus S minus 1. This is what you call a flat factor, okay? So the symmetric space definitely does differ when you go from semi-simple to reductive. So there's a classification theorem. It goes back to Cartan, E. Cartan. So they split as a product of 3 types, what's called a non-compact, a compact, and a Euclidean symmetric space. So the Euclidean one is just Euclidean space, so there's not really much to say about that. But the other ones are more interesting to classify. And it turns out, and I think this was maybe even a surprise to Cartan, although who knows, but it follows the classification of simple real Lie algebras. So you get the usual types, A through G, and there are various subcases. So if you classify simple complex Lie algebras, you just have the types A through G. But when you look at real Lie algebras, you have various subcases, because there's things that happen over the real numbers that disappear when you pass the complex numbers. You already can see that already with bilinear forms. There's no, over the complex numbers, if you have a symmetric bilinear form, it doesn't have a signature, but you have that over the real numbers. So that's why you have OPQ versus ON. Okay, so there it's if you look in Helgeson's book, you can see a big table. That's one of the standard references for trying to learn this stuff. And you can see that it's rather intricate, but it's also not that bad. It's sort of a finite list that's with a lot of nice examples. So typically, this space, in contrast to what you might be used to for SL2 over Q, this symmetric space is just a manifold, a real manifold. It doesn't have a complex structure in general, but sometimes it does, and those have a special name. They're called Hermitian symmetric spaces or bounded symmetric domains. So just to give you in there, you can look in the table in Helgeson and see which ones are. You just have to look at the various data coming in the classification and see what's going on with it. So for example, SL2 and SP2N are, but SLN is not when N is bigger than or equal to 3. So for example, SL3, this global symmetric space is 5-dimensional, 5 real dimensions. So it can't possibly be a complex manifold. And this classification into Hermitian and non-Hermitian can seem kind of random. So for example, SO2n is, but if you have SOMn where neither one of those is 2, I don't know if that's what I've written there, but what I mean is that you don't have a 2 there. So then that one is not. So it can seem a bit random which ones are, which ones aren't. But so from the practical point of view, the most interesting thing for us is that SLN is not when n is bigger than or equal to 3. And certainly SL2 over an imaginary quadratic field is not. This was discussed this morning. Okay, now locally symmetric spaces. So the arithmetic group gamma acts on the symmetric space because G acts on the symmetric space, so we just restrict the action to gamma. And the quotient is called a locally symmetric space, okay? If it happens to be Hermitian, then this has the structure of a quasi-projective variety, but in general, it's not. In general, it's just, it has no complex structure. So here are some examples. One that I'm sure you've seen, if you take SL2 over Q, and then we take the Hecke congruent subgroup, then we get the modular curve. Now this is what sometimes is called the open modular curve because it's not compact. This is not a compact algebraic curve. It's missing some points. It's a compact algebraic curve where you've put some punctures in it. If you take the restriction of scalars from SL2, where F is totally real, then the global symmetric space was D copies of the upper half plane. And gamma acts on this by the different embeddings of the field F into R. So gamma, F has D different embeddings into the real numbers, and we can take SL2 OF and embed that in D different ways into SL2 R. And so that's how it acts on those different factors. This quotient is an algebraic variety. It's called a Hilbert modular variety. And it's one of the first generalizations of the modular curves. It's a very interesting collection of algebraic varieties. If we instead do GL2 instead of SL2, again with F totally real, the symmetric space globally is D copies of the hyperbolic plane again, but we have this extra R to the D. I think that should be R to the D minus 1, sorry. We have extra R to the D minus 1. And then when we take a quotient by an arithmetic group, we don't get a Hilbert modular variety. We actually get a torus bundle over Hilbert modular variety. So that extra flat factor, the action on that is really coming from the units acting on it. And so when we take the quotient, we get a torus. So because there could be some twisting in this, it doesn't have to be a product of the Hilbert modular variety with a torus. We could get a non-trivial fiber bundle over it, okay? So of course, in that case, it's not an algebraic variety anymore, but it's pretty close to one because sitting under it is this Hilbert modular variety. Okay, finally, we get to cohomology. So if our group gamma is torsion-free, then when we take the quotient y gamma, remember that's gamma divided into D, that's going to be a manifold. In fact, even better than that, it's what's called an Eilenberg-MacLane space. So the fundamental group of that quotient is isomorphic to gamma, and there are no higher homotopy groups. They all vanish. So in this setting, we have something like a geometric incarnation of the group gamma. And the group cohomology, which you learned about last week, with gamma coefficients in Z, is isomorphic to the integral cohomology, of singular cohomology of this quotient y gamma. Okay, so this is not the algebraic way to define group cohomology. It's actually one of the first ways, probably the first way. To me, the history is a bit obscure, but I think it is the first way that cohomology of a group was defined. Be bold and say that. Now there are more algebraic ways, but from a geometric point of view, this is still a very nice way to study these things. Okay, now most of the time we're interested in spaces in gammas that have torsion, not in torsion-free ones for various reasons. But in that case, these statements just simply are false. So first of all, y gamma is typically not a manifold. I mean, it is in some cases, but in general, it's not. It's what's called an orbifold. So this is a singular space. So locally, it doesn't look like Euclidean space, but it looks like Euclidean space divided by the action of a finite group. So sometimes this is called a V manifold, but I think the common terminology today is is an orbifold. And so then, okay, it's not a manifold. That's too bad. And in fact, another thing is that if you look at these two sides, the right-hand side could vanish where the left-hand side is not supposed to vanish. There could be group cohomology in degrees where there's no singular cohomology for that quotient in the same degree. So that's a problem. Certainly that isomorphism can't be true in that case. But as it turns out, as long as we're willing to ignore this torsion coming from finite subgroups of the group gamma, say by working with rational coefficients or complex coefficients, this isomorphism is still true. Even though Y gamma is not a manifold, and even though over Z, gamma could have cohomology in degrees outside that of the dimension of Y gamma. So, and that's usually what we do. And this does have, it's not ideal. It's certainly not ideal. It would be much better to be able to work with Z and to work geometrically on the right-hand side, in my opinion, but I don't think we really have a good understanding of how to do that. So in general, for applications, we need to consider more than just integral coefficients. We need to consider coefficient systems or twisted coefficients. So if you have, in the general setup that we tend to work in, you take a finite dimensional rational complex representation of the group of rational points. So that just means you think about the classification that we were writing down before, and examples with SLN, SP2, and usually just means you take one of your standard representations that you know from your course on Lie groups and Lie algebras, and you just now look at it restricted to the group of rational points. So for example, the standard representation, symmetric powers, exterior powers, things like this. Then this gives a Z gamma module, so we can compute the group cohomology with coefficients in that. And on the quotient Y gamma, we get a local system, twisted coefficient system. So I don't want to explain exactly how this works, but if you want to learn more about homology or cohomology with twisted coefficients, and there's the classic paper of Steenrod talks about it, and it's also discussed in Bott and Tu's book on differential forms in algebraic geometry and algebraic topology. Okay, so if we really need to work with this kind of general coefficients to be able to have the most applications, and these are the spaces that where the automorphic forms live. So it's a conjecture of Borel and theorem of Franke that these spaces are built from automorphic forms. They're not all of them, not all automorphic forms are going to show up, but all of these spaces are sort of intrinsically tied to automorphic forms. Okay, so these are the spaces really that we're interested in investigating computationally and trying to understand connections to the various things that we discussed on the first slide. So here's an example, which again, I think many have seen, probably everybody, but I want to just talk about it. So in the case of classical modular forms, which sort of motivates this whole story, the symmetric space SL2R over SO2R is the upper half plane. Our group gamma is the Hecke congruent subgroup of things that are upper triangular mod n. And then the quotient Y gamma is open modular curve. So in this case, we're going to let E be the degree K minus 2 homogeneous polynomials with complex coefficients. Okay. So the group GQ acts on this. In fact, complex points acts on this by change of variables. You just replace XY you act on them by your matrix. Think of XY as being a vector, and you want to be careful, you have to act on it by the transpose. But in any case, there's an action on that coefficient system, and that gives a structure of a Z gamma module. If you take the cohomology in this case, then what you find is that H upper 1 is isomorphic to the following. You have SK of gamma, which is this holomorphic weight K modular forms on the group gamma, added together with the complex conjugates of those. And then you have another summand, which corresponds to weight K Eisenstein series. So when you have SL2, when you have gamma, let's say when you have the full group SL2 of Z, then there's no weight 2 Eisenstein series, say when K equals 2. But in general, even for K equals 2, for higher levels in, there could be non-trivial contribution to there. Okay, so but this is the sense in which this cohomology group, cohomology space, is built out of automorphic forms. There they are, they're sitting there, automorphic forms, like the best kind, the holomorphic weight k modular forms where k is bigger than or equal to 2. Okay. And so, and what's the connection? Well, for Cuss forms, it's actually, you just take the modular form, which is function on the upper half plane, and you make a differential form on the curve. You just take f to f of z dz. And so this is what you do for weight 2. Okay. I didn't say that in that statement above there, but this is what you do for weight 2. If you start with a Cuss form, which means a modular form that vanishes very rapidly at infinity, then when you make a differential form out of it, you'll get a holomorphic 1 form on the space. And you know from algebraic topology using the de Rham theorem that that's one way to compute cohomology. So at least here it seems reasonable that there's a way to go from a modular form, i.e. automorphic form, to something cohomological. And some more remarks about this is that if you only use twisted coefficients, you will only get the weight 2 modular forms. Those are great, but we really want all of them that we can make. And we need to use those coefficient modules to get the higher weight ones. If we instead, in addition, we want modular forms with character, we can use this other congruent subgroup. We don't have to use gamma naught of n. Those are the ones that give us modular forms of trivial character. If we want more interesting characters, we can use gamma 1 of n. So these are the subgroup. This is a subgroup congruent to the identity, or upper triangular unipotent mod n. And the last two things are pointing out this fact that not every modular form is going to show up. So the weight 1 holomorphic forms do not appear in cohomology, and the Moss forms, the real analytic forms, don't appear. It doesn't mean that you can't use cohomology in a sense to study these. So for example, weight 1 forms, they are part of the ring of modular forms of all weights. And so you can sometimes take, if you have a weight 1 modular form and you multiply it on a weight k1, you'll produce a weight k plus 1 modular form. So that means you can see that weight 1 form using that k plus 1 form in the k form. So those are, of course, cohomological. So there's going to be some shadow of the weight 1 guys appearing in there. And then there are various ways to think cohomologically about Moss forms, but they don't follow this sort of classical framework that I'm talking about now. And what we're talking about, they will not show up. And again, this is very, I'm sure I'm repeating a lot of what Haluk already said, but in any case. So to end the last few slides, I just want to say in general, why, so that explains what happens for the holomorphic modular forms, why of weights bigger than or equal to 2, but why in general should automorphic forms have anything to do with cohomology of arithmetic group? I mean, it doesn't. In that case, there was sort of a relatively direct connection, but why in general should it be true? Why is Franke's theorem true? Well, it's actually a version of the de Rham theorem in disguise. It's almost the same idea that we talked about for the holomorphic modular forms, but it's definitely ramped up quite a bit. So let's just, to explain sort of the general idea, which I think is important to know, let's look at the semi-simple case, and we'll look at the trivial coefficients case. It's not that much more complicated to deal with coefficient systems, but we might as well just, it's more familiar to work with trivial coefficients. Okay, so first of all, what is an automorphic form in general? So what's the general way to think about it? So this is not the most general, and it's a relatively classical way to think about it. It goes back to Harishchandra, and there's a nice paper by Burrell and Jacques in the Corvallis volume talking about this, but it's essentially the same as whatever other way you want to think about these things. So look at so remember, G is the Lie group. It's not the algebraic group. So you can think of G as being like SLN R or something like that. Take the smooth functions on this Lie group G that are gamma invariant. So the smooth functions on G divided by gamma on the left gamma invariant. The automorphic forms sit inside there, and they are the functions that satisfy the following properties. So they have to be right k finite. If you take these functions and translate them on the right by k, then you get a finite dimensional space. And they are, so by construction, they're gamma invariant on the left. So you see that doesn't interfere here because K is acting on the right. And they're left ZG finite. So this Gothic G is the Lie algebra of G, and ZG is the center of the universal enveloping algebra. So if you haven't seen that before, you can just think of it as the following way. These are, there's a nice collection of differential operators on these functions. In fact, they're the invariant, the bi-invariant differential operators on G. So this saying that it's left ZG finite just means that there's some collection of differential equations that it satisfies. I mean, that's, you can certainly say something is holomorphic using a collection of differential equations. It's a generalization of that. Like, what's the natural generalization of that when you replace G by SL2, by SL2R by a general group G? And we also want growth condition. We don't want the function to grow too rapidly as you go to infinity. And it's kind of technical to say what it is, but you might probably be familiar with that in the case of modular forms anyway. Okay, so let omega p, it should be upper p, sorry, be the holomorphic p forms on Y gamma. So Y gamma is a double quotient because it's the quotient of D on the left by gamma, so it's a double coset space, G mod K on the right by gamma on the left, okay? So we're looking at the differential P forms with complex values on that space. Now, this description of the key here is to identify those P forms with the object on the right. The K HOMs from the Pth exterior power to that funny looking letter on the other side of the slash is actually a K. It's the Lie algebra of K. So we take the Lie algebra of G divided by the Lie algebra of K, and we take the P forms on that. So this G, so the Lie algebra of G is the tangent space at the identity of the Lie group G. So actually what this G, Gothic G divided by Gothic K is, it's really the tangent space at the distinguished base point of Y gamma. That's all it is, just written in terms of the Lie algebras. And so we're taking the Pth power there, Pth exterior power. So that should immediately suggest that we're doing something with P forms. And we take K invariant maps to equivariant maps to C infinity G divided by gamma. Okay, so there's a bit to unwind there, and I don't have time to say much more about it, but at least if you know that, okay, P forms have to do with antisymmetric functions on tuples of tangent vectors, and you also know that the exterior Pth power of the tangent space is related to that, and you know that there's a K action involved, you can probably believe it at least for a few more minutes. Okay, so that right-hand side now is actually a complex if you vary P, because you have a differential, you have the usual de Rham operator on the P forms, and that gives you, if you have this identification, it gives you a differential on that, okay, that goes from P to P plus 1. You can either get the differential that way, or you can give a direct definition of a differential in terms of relative Lie algebra cohomology. But in any case, you can turn that guy on the right-hand side into a complex, and that complex computes the cohomology of gamma with coefficients in C. Okay. But now, because you have, if you go back and look at that, you have the C infinity of gamma G there, and we have the automorphic forms sitting inside that, we can just include them in there. So the automorphic forms include into C infinity of G divided by gamma, and Franke's theorem says that that inclusion induces an isomorphism on cohomology. Okay, and it was a very big theorem, very difficult and deep theorem, proved in the late 90s. And had been conjectured by Borel quite a bit earlier. Okay, so in a precise sense, you are computing with automorphic forms when you're computing with cohomology. Franke guarantees that. We can do similar things for coefficient systems. We just have to ramp up our notion of what a differential form is by making them E-valued instead of just C-valued. And this also gives a way to say a little more about why certain kinds of automorphic forms appear and other ones don't. So it depends on, you know, once you've So associated to automorphic forms, you have something called automorphic representation. And I definitely don't want to get into the details about that, but such a thing splits over the places of the field that you're considering underlying everything. And there's something called the infinity type, which has to do with the Archimedean places. And there are very strong restrictions on when, on the Archimedean, on the infinity type, as to when that complex can have non-trivial cohomology. So for example, there's a classic paper of Vogel and Zuckerman that writes down conditions telling you when this can happen. Okay, and this is why, like when Haluk was saying, you have to have discrete series, and you can't have a limit of discrete series. Discrete series corresponds to weight 2, and then the limits of discrete series corresponds to weight 1. You can't have those. Okay, but at least one nice thing about the ones that do appear is that we expect them to be related to arithmetic geometry. And in a lot of cases now, we can actually prove that that's true. Okay, so that ends the first talk. Sorry, I use stuff all the time.
Are there any questions for Paul? Yeah, here's the question.
Yes, just about the comments of the notion of algebraic torus. So why do we name it torus? I mean, what's the link with the asymptotic?
I'm sorry, I can't. Could you speak a little?
So the question was, why is it called a torus? Why is the algebraic torus called a torus?
Because it is a torus. I think the better question would be, why is the thing that looks like a donut called a torus?
Yes.
So the reason is, okay, so I'm being a bit silly, but so for a compact group, it is a torus. Like if you take a compact group like the unitary, like SUN, something like that, then this is actually the compact torus that you're used to. But when you go away from compact groups to non-compact groups, the gadget that plays the same role is going to be this thing that we're talking about now. Like one way to study representations of SLNC is by looking at representations of SUN, like so-called Unitarian trick by Weil. And you see that structurally this thing that I called a torus is giving you the same kind of tool that the other thing is in the compact case. So that's one reason. But another reason is that the compact torus, of course, is inside there. I mean, if you take C cross to some power, then C cross can be written as S1 times R bigger than 0. So if you sort of squash away that R bigger than 0, you see the compact torus sitting there. So I don't know if that's a sort of a useful answer, but that's why it's called a torus. I think that's one explanation.
Thank you. Can I ask us a stupid question? So you had 2 times where you were referring to Lie algebras, just because I'm not always working with them. Can you go back maybe to there? So for SLN, you would get the Lie algebra is
trace 0 by n matrices.
Yeah, what would be Z? What is the universal enveloping?
The universal enveloping algebra is so you take the tensor algebra on the Lie algebra, and then you mod out by the ideal A tensor B minus B tensor A equals the bracket of A and B. So it's an associative algebra that you build out of the Lie algebra, and its representations as an associative algebra are the same as the representations of the original thing as a Lie algebra. So it's a way to go from the Lie algebra, which is not an associative algebra because it has this Jacobi identity instead of being associative, is there sort of a replacement for being associative, to an associative algebra. So I think the easiest case to understand it is if you look at SL2R, then there's a unique generator, that's sort of a unique differential operator that's relevant here. It's the Laplacian on the upper half plane. That is the that is the operator that you get from ZG.
Okay, and then in the next slide you say G mod K.
Yeah.
Can you say what that would be for SLN?
Yeah. So for SLN, G Gothic G is the trace zero matrices. For the orthogonal group, for the special orthogonal group, you get the skew symmetric matrices. So so the condition of A times A transpose is the identity becomes that A plus A transpose is 0. So those are the skew symmetric matrices, n by n skew symmetric matrices. That's what K is.
So then the quotient would be upper triangular matrix,
Right.
0 on the diagonal.
Right.
Okay, thank you.
And so it's because the tangent space of the identity of G is fancy G, and the tangent space of the identity of K is fancy K. So that quotient is the tangent space to G divided by K.
Thank you. That helped me a lot.
Okay. Yeah, the last bit was rather quick, but.
Are there any other questions? If that's not the case, let's thank Paul again.